in the last class we have already seen how from DTMC description we can go to continuous time description. Okay. So, we have derived the Chapman Kolmogorov forward equation. We have also seen a very important matrix that characterizes a continuous time Markov chain, which is called the rate matrix or rate transition matrix. So, that is something also we have characterized, what are each of the term of rate transition matrix, what is the row sum of that matrix. So, these are the things we have already characterized. Now, with that we are well equipped to go towards actually deriving the theory of CTMC. So, today what we will try to see is get the basic governing equation of CTMC for of course again stationary case and homogeneous case of course. So, that will do and we will try to see the application of that. So, in the previous class if you see, that was our characterization of rate and as well as this is the Chapman Kolmogorov forward equation. Okay. So, this that is how HST has been characterized. Okay. Now, let us try to see how do we move from this transition to state. Okay. So, it is a Markovian process. So, suppose I am at some 0, I have or let us say not let us not talk about 0, let us say even 0 is okay. So, at 0th time I am at pi 0, that means this is the state probability. So, of course, pi 0 is a vector which is having pi 1 0, pi 2 0. So, this is the time index at time 0 and this is the state index. Like this, as many states are there, if there are n number of state, this will be the case. Okay. So, this is the state matrix. Okay. We have seen a simple relationship between the state and the transition. If we multiply state with transition matrix, state vector with transition matrix, we go to the next this one, that is pretty straightforward. So, basically if I know pi 0 and I know the corresponding transition h 0 t, okay, s I am putting 0. So, that is why I told it can be even generalized to means s also. So, this might take me to pi t. Okay. So, this is well understood, this will be happening always. So, basically it is currently I am at this state, this is the transition probability. So, if I multiply I see where I will be going at time t. So, that will be the our probability state probability at time t. This is a well understood fact. Now, if I differentiate this with respect to t, then what will happen? Pi 0 do not depend on t. So, therefore, pi 0 comes out. Okay. So, this will become d dt of h 0 t. Now, I will put this from the Chapman Kolmogorov forward equation by putting s equal to 0. So, what do we get over here? Del del t of h s t is nothing but h s t q t. So, I can write that. This is something I can write. Now, what is this? Again from this definition, that is pi t. So, therefore, I can write del del t of pi t is nothing but pi t into q t. That is the fundamental state equation or differential equation that describes the state. Okay. So, what it says is the time differentiation or rate of change of the associated probability is nothing but the current probability into the Q matrix, the rate transition matrix. Okay. This is what is the fundamental to CTMC. Now, what we can do is something we have done earlier also. If we take homogeneous assumption, immediately Q t becomes free of t. it becomes q, because that is not varying over time. So, I can write this del t of pi t is nothing but pi t into q. Now, if we take another assumption of stationarity, then immediately the state also will not be changing over time. So, that will become some pi, and this rate of change of those associated probabilities also will not be changing. So, that becomes 0. So, I can get a very simplified equation pi q equals to 0, almost like DTMC. In DTMC we had pi p equals to pi. So, similar equation we are getting over here, which is pi q equals to 0, and of course, the associated state probabilities have a normalization. So, pi I is equals to 1, I equals to 1 to n if there are n state. So, again set of linear equation. So, n number of, because this is n dimensional matrix. So, n number of linear equation over here and one equation over here, you can solve those linear equation and you can get the associated probabilities, state probabilities. So, now we could derive our continuous time Markov chain associated equation also, and this will be our governing equation. Remember, these equations are only true if it is in stationarity or it has been stabilized. Okay. If it is not in stationary, then it will be governed by this differential equation. You can also do that. In transient Markov chain, you will be always able to get the corresponding differential equation, and then there will be set of differential equations. So, you will be having n number of differential equation, all has to be solved the way we have done for Poisson. Basically, Poisson was similar to this one. So, you can even solve Poisson process by this analytical term also. We have done it from first principle, but same thing, same equation you can derive from these set of equation, and then recursively you can solve, you get Poisson process. Just the Q matrix has to be properly populated. Okay. Can we just do a little exercise over here? Can we just try to see what should be the Q matrix for a Poisson process? What is Poisson process? It is a pure birth process. That means every time somebody is just arriving, it is just an arrival process, there is no departure, so there is no death as such. Okay. So, people are just arriving and it is the count of that. So, Poisson process is all about that. So, if it is a pure birth process with arrival rate lambda, can I now talk about my Q matrix with the non-symmetry principle and everything? Okay. So, now Qij I know. Pure birth means every time I, due to non-symmetry principle, only one arrival can happen, only I can go to I plus 1, nothing else. So, whatever state it is there, it can only go to the next state. Okay. So, if there are one customer, the next time it can only go to its count can go only to 2. If there are the count is 2, it can go to 3. So, this is the only allowed transition or rate, associated rate, and what is that rate? That is lambda. So, therefore, if you see this is the diagonal one, only this off diagonal will be populated with the value lambda. So, that only that off diagonal will be having value lambda, and all other things other than the diagonal I will come to later, other diagonal will be all 0. Okay. If that is the case, I know this sum of rho, what that should be? That should be, definitely that should be 0, we have already characterized it. So, if that is 0, so therefore, this diagonal term will be all minus lambda, that is all. And what will be the size of that matrix? It will go to infinity, because the count goes up to infinity. Poisson, when we started deriving, it is an infinite matrix. So, put this Q matrix. So, now you can see how to derive a Q matrix. For Poisson, we have now derived the Q matrix. Put this Q matrix over here, formulate those differential equation, you will see that exactly what we have derived for Poisson, whatever differential equation we have formulated, those will be derived over here. Okay. That is the strength of this theory. So, we have done this theory in a different manner, whereas while deriving Poisson, that was directly done from intuition. Of course, the same principle were taken into account. It was also taken into account over there, stationarity was taken into account. Over here also stationarity we are kind of taking into account. Okay. So, that Markovian was taken into account because Chapman Kolmogorov comes directly from the Markovian property, that was taken in, and non-simultaneous is taken into account because for defining the Q matrix we are doing this non-simultaneity principle. So, all those things are actually taken into account, and with that we are trying to derive this. Okay. So, you can take this as home exercise and try to see whether this is exactly matching once we get this Q matrix, whether it is exactly matching to our earlier derived Poisson things, okay, Poisson equations. But having said that, now we have got the governing equation. This was just a check of that governing equation. So, basically as you can now see, all our target will be get the correct system description and get a correct Q definition, the associated rate definition. This is what we will have to do. So, our next onwards whatever we will be deriving, our time will be occupied with this thing only. How do I get the Q? What's from the system description, how do I populate the Q matrix terms or elements? Once we put those terms, then it is just solving the linear equation, nothing else. Okay. With this background, let us try to solve some realistic things in queuing. So, we have so far talking about queuing, so we still have not solved any queuing. Let us try to solve a queuing system with a single server. So, only one server is there, okay, which has some description. What are those description? That the arrival process follows a Markovian process, okay. So, it is a Poisson arrival with rate lambda, and the service process, that is also all, and they are independent, arrival to service they are independent, and each service also independent, they are identically and independently distributed, and they follow again a exponential, which is a memoryless process, exponential distribution. Okay. So, this also follows an exponential distribution with service rate, that exponential parameter is mu. Okay. So, arrival rate is lambda, service rate is mu. So, these are the two things we have. Okay. And we also know that there is only single server, Q is FIFO, first in first side, first out, and the Q length, how many customers it can hold, that is infinite. Okay. So, these are the description which has been given. Now, this Q we will try to analyze. We have done earlier all those means time keeping of the events, related events that will be occurring. So, those things we have done. We have also understood that if all these service and arrival are Markovian, then I do not have to really keep track of those residual time. So, I can actually describe this system with the state description, which is number of customer in the system. So, whenever you do this analysis, queuing analysis, the first thing you have to come up with the proper state description. The state description should be in such a manner that summarizes the whole thing. It is not leaving anything. If it is leaving anything, then the next step I want to describe, it will not be just dependent on that, something else it is dependent on that you have not given in your state description. So, I have to be careful while describing the state or defining the state. So, over here, because of all these Markovian, nice Markovian property, and we have seen that it is memoryless and the residual time is also similarly exponentially distributed. So, basically any time I try to observe, I can count all of them as number of customers. I do not have to see how much residual time he has been served. So, those memory I do not have to keep. I can just take them as number of customers, and number of customers solely describe my whole state. So, therefore, my state description will be only number of customers in the system or number of packets in the system. So, this can start from 0, it can go to 1, 2 dot up to infinity, because now again another description comes into picture, because this can hold up to infinite number of customers. So, therefore, the state can eventually go up to infinity. If I would have said that buffer has a limitation, that it can only hold this many data. So, let us say I have some m number of data it can hold, then the state will definitely go up to m, because beyond m it will be all dropped. So, it cannot hold in the system. So, system can only hold if buffer is m, of course 1 can be in the server. So, m plus 1, up to m plus 1 only it can go, only that many customers or that many packets can be there in the system. So, again the description of the system comes into my state description, as you can see. Okay. So, this is the whole description of the state. Now, I have defined the state. Can I now define the Q matrix? Okay. Because it is a continuous time Markov chain, any time it can do arrival, any amount of service can be required. So, any time it can do departure. So, all those things can happen. So, it is a continuous time Markov chain or Markov process. Now, let us try to see, can I define my Q matrix? Okay. So, what is the Q matrix? Let us try to understand this now again. Remember, those non-simultaneity principle will be always very handy. In the queue, can you see at any time if it is in state I, what can happen? So, suppose I observe the system at time I. So, at this instant, in the next future, what can happen? Either it can stay in I, that is okay, nothing happens, nobody arrives, nobody departs. So, it stays in I, or it can happen that immediate next time one arrival happens, then I will go towards I plus 1, that is valid. And if there might be also a possibility that a particular person who is in service, his service gets over, then I will go to I minus 1. Nothing other than this can happen, only these are the possibility. Either at a particular time instance it can increase the state by 1 only, because of non-simultaneity principle. Simultaneously two arrival cannot happen, simultaneously arrival and departure cannot happen. So, it can only, means what it can do is it can only either increase the state by 1, that is the possibility, or it can decrease the state by 1. These are the only two possibility, nothing else. If that is the case, if I see this Q matrix, again I can infer that, okay, diagonal, you forget about that, diagonal means we populate it separately, because we know the row sum is 0. So, therefore, off diagonal if you can populate, immediately diagonal will come, because it is complement to that. Over here, what will be mostly populated? I know only these two transition. So, off diagonal this one off diagonal and the lower off diagonal, that is the only thing which will be populated. And what is the state dimension? That will go up to infinity. So, it is an infinite dimensional matrix. So, only the off diagonal one will be populated. So, if I just start putting, what will have value? So, this is, let us say it is start from 0, 1, 2, 0, 1, 2, goes up to infinity. Okay. So, 0, 0, that is the diagonal term, I will not be concerned about that, but 0, 1, 0 to 1 means what? It is in 0 state, one arrival happens. So, that must be populated, that is possible, one arrival can happen. What is the associated rate of arrival? That is lambda, and all others will be 0, because I know due to non-simultaneity principle that cannot be populated. Then what will be 0, 0? This sum should be 0. So, therefore, this must be minus lambda, immediately I can do that. Okay. Again this diagonal term I will keep it. What will be this? 1 to 2, 1 to 2, that means one arrival, again with rate lambda. Okay. 1 to 0, that might happen due to departure. Now, let us try to see, there is a single server, one server is there. That server, what is the associated departure rate, or let us say means this particular rate, that some customer will be departing from there, that will be populated over here 1 0, because it is in state 1 and it is going to 0. What is the associated rate? That is what we want to try to characterize. Let us see in server what is happening. So, whatever the server is, so server, suppose I am at time t, the server might have taken the nth customer or let us say kth customer, at some earlier time, let us call that t minus 1, okay. Some earlier time it has taken that customer and it is servicing it. At time t I see that it has serviced some amount of time. What is the residual time? That is still, because of exponential distribution, this is still exponentially distributed with parameter mu. So, therefore, what is the associated rate that it will be completing the service? Associated rate is mu, because with mu rate it service, the server service the things with rate mu. So, therefore, associated rate is mu. So, with mu rate, because of this exponential distribution, that nice these things, I could get that even whenever he arrives, it does not matter, wherever he intercepts the packet, the residual time, rest of the time he can just forget about the past, he can again infer that the residual time will be still having a service rate with mu. So, therefore, the rate at which the customer will be departing is mu only. So, this will be mu, then what will be, all other things will be 0, of course they cannot. So, what will be the diagonal term? Because this should be 0, summation should be 0. So, that should be minus mu plus lambda, and you keep doing accordingly. So, next this term will be lambda, this will be mu, and this middle term will be minus mu plus lambda, and all others will be 0, and so on, it will keep on get populated. So, that is my Q matrix. So, I have characterized my Q matrix. All now I have to do is this, if I have to solve it, this should be pi q equals to 0 and summation pi i's is equal to 1, I equals to 1 to infinity, sorry, now 0 to infinity. Okay. So, these two, there will be infinite linear equations. If I just recursively solve them, I will get my things done. So, this is easy. Now, we know how to solve it, but before doing this, let us try to also make life little bit more easier, and that you will also from there you will be able to appreciate why this is actually called a Markov chain. Okay. We have talked about Markov process, but it is also called, we have been keep on telling that it is a Markov chain. So, let us try to appreciate what chain do we have. So, basically it must have a graphical representation and it will have a chain like graph, that is what it will be. Let us try to appreciate that part. What I will do now, this state transition I can graphically represent. So, each node will be the states. So, 0, 1, 2 up to infinity, okay, n plus 1, n minus 1, something like that. Okay. So, this is the graph of state where nodes are represented by the states. Now, the transition, which is the effective rate, that will be represented by the arc or the link between them. Let us try to see what are the transition which are valid from here. So, there is a transition from 0 to 1. It is a directed graph, of course, because the transition has a direction, it goes from one state to another state. So, therefore, it is a directed graph. So, 0 to 1, that is possible. 0 to 2, is that possible? No, because means this is not allowed due to non-simultaneity principle. Two arrivals simultaneously, 0 to 1 means it was in 0 state, one arrival has occurred and it has gone to 1 state. From 1 it can go to 2, from 2 it can go to 3 and so on. N minus 2 it can go to n minus 1, n minus 1 to n to n plus 1, n plus 1 to n plus 2, like this. And also there might be a backward transition. So, from 1 with the departure it can come over here 0, from 2 it can come to 1, and that is the only transition which are allowed. So, as you can see, it actually construct a chain like graphical representation. So, that is why it is called Markov chain. So, this chain is represented as Markov chain, and in the arms we in graph we actually in the link we give some cost, over here we can give the rate. So, this has a rate lambda, this has a rate mu, this has a rate lambda mu, lambda mu. This summarizes the Markov chain. And all these equations, so this pi q equals to 0, what does this tells actually? It is actually tell that this 0 means this was actually del pi del t, right, rate of transition, rate of change of as if the probability. So, this nodes are as if having this probability value. So, let us call that pi 0, pi 1 and all those things, and then what we are seeing that with this rate it is either going out those probabilities, as if probability is some entity with some rate it is going out to other states and it is getting populated also from other states, and this rate of change of this probability value, as if probability is some entity which is getting out from one container, this is that node 0. So, pi 0 has some probability and it is going out, and from container 1 probably some probability is also coming in, and accordingly over time this probability is getting populated. It is like some container and some liquid is going out with some rate, some liquid is coming in with some rate, and I am getting the overall amount of liquid. Okay. So, you can think it in this analogy as if some probability is going out with some rate and some probability is coming in with some rate, and that net rate from any state is actually 0, because this is all 0. So, this part is all 0 due to the stationarity. So, therefore, if I construct a case of this state 0, so total outgoing and incoming rate must be balanced. That is the stationary condition, and that is the governing this equations. So, what I can say over here is lambda into pi 0, that is the overall rate of outgoing probability, must be equal to, that must be balanced by the incoming probability, which is actually mu into pi 1. That is first equation we have got. If you see this pi q equals to 0, if you put the first equation, you will see that that same equation will be formed over here. Okay. So, you will be able to see that. Okay. So, if you put pi q equal to 0, you will see this equation will be formed, the first equation for the first row. For second row, you will see the second equation. Okay. So on you will be able to derive this equation. So, basically everywhere for node 1, if you construct this one, that for node 1 all the outgoing rate must be equal to incoming rate. So, all the outgoing rate is, this one is outgoing, so which is actually lambda into pi 1. This is the outgoing one, which is actually mu into pi 1, that must be equal to all the incoming rate, which is lambda into pi 0, wherever it is coming from with that rate you multiply, lambda into pi 0 plus from here something is coming, so which is actually mu into pi 2, that is the second equation. You will again see that second column will be actually forming this equation, and so on, we can do that. So, all these balance equation can be very nicely constructed from the chain itself, we do not have to really go into that. So, if I can construct the corresponding chain, I do not need to completely construct the whole Q matrix and then construct each of these equations. Not only that, there is also a simple simplification over here. I can, because it is rate balanced of those probabilities, so I can construct any combination of state as a combined state. So, suppose let us say 0 and 1 I put as combined state. Then from this combined state all the outgoing rate must be balanced again with the incoming rate. So, therefore, just this and this must be balanced. So, immediately I get an equation which is lambda into pi 1 must be equal to mu into pi 2. If you see, I put this over here, I get this equation back. So, I get this simplified equation if I can study the Markov chain properly. So, all next time onwards we will be doing, we will be putting this system to Markov chain description and then do the analysis, steady state analysis. So, that will be our next task. We'll in the next class we will try to see construct those Markov chain, and very quickly we will be able to construct those Markov chain which are linked to our trunk switching. So, we will do our trunk switching analysis. Now, we are in a place to do the trunk switching analysis. Okay. Thank you.